Hello, everyone. Welcome to this video. This is the first part of my talk at the NCNGT math conference. It will be about Hitchin representation in a lattice and will be divided in two parts. The first part will introduce the notion of Hitchin representation and of a lattice of a Lie group. And in the second part, we will give context and motivation for the problem and explain what is known about Hitchin representations that lie in a lattice. So I will define everything. First, before starting, let me thank the organizers for inviting me to another section of the NCNGT conference. Okay, so first I'll define what are Hitchin representations. So we consider a connected closed orientable surface of genus G at least two. So these are just like surfaces that look like this. All right. So they are closed, mean they are compact and they don't have boundary components. They do not look somewhere like this, for example, like a tube. We exclude those. The genus here refers to the number of holes here. So we want at least two of them, because if they have at least two, then they have a hyperbolic metric. We'll explain, it will come into play in a minute. So these are surfaces, so they are two-dimensional as manifold. So in the picture here, this has like here you can see locally it's a plane. Like imagine that the interior is empty. Like we're not talking about something solid. We're talking about something that is empty inside. So we want it orientable so that they all look like the picture I drawn, and in one part, so connected. Okay, so its fundamental group has a very nice description as I written here. So we will have 2 to the 2G generators in these presentations, and they all satisfy one relation. There is only one relation. And for the notation here, A1, B1, for example, is equal to the commutator. So it's A1, B1, A1 inverse, B1 inverse. So we want the product of all commutators to be equal to 1, not all commutators to be equal to 1. Only the product of all of them must be equal to 1. So this is the fundamental group of the surface, and it encodes the topology of the surface. And here we are really focused on the geometry we can put on the surface, and there are various of them, and sometimes even if we restrict the geometry we want, like they can be infinitely many. But what will allow us to understand which one we can put, that would be the properties of the fundamental group, so the topology of the surface. So for this, we'll look at the special space, which is the space of homomorphism from the fundamental group to a group G. So just group homomorphism, but when G is a topological group, this will have a topology. And how? So the idea is that we can embed this space into G to the 2G by taking a representation rho and mapping it to rho A1, rho B1, up to rho BG. Like we just say what are the image of the generators, and if two representations agree with this map, then they must be the same representation. So like we embed this space in G to the 2G, which has a topology. We assume that we are talking about a topological group, like a group of matrices, where the topology is determined by how close the coefficients of two matrices are. And thus the D space as the subspace has a topology. So basically, it just means that a representation converges to another, like a sequence of representation converges to a representation rho infinity if for all if for like A1, for example, the sequence of rho n A1 converges to rho infinity A1. And we want this, but we also want all of those. So up to rho n, up to Bj. So we want convergence on the generators. So we have a big topological space that might be not really, might not look good, but at least we have the notion of converging, so we can talk about continuous function and stuff. And we also have a notion of deforming representation. Like we can say that a small deformation would mean something that lie in a neighborhood of a representation. So we have this particular topological space, and it's quite interesting since already for G equal PSL2R. So let me just recall that PSL2R, this is SL2R quotiented out by plus or minus identity. Okay, so consider it to be SL2R, but it's not. So this space has 4G minus 3 connected components. So here the connected component depends on the genus, but I'm going to give the example when the genus is equal to 2. So here we will have 5 connected components, and they are labeled by an integer. Here will be 0, 1, 2, minus 1, minus 2. And the two extremal components really play a special role, since let's call them C2, C minus 2, which I mean the connected components labeled by 2 and the connected component labeled by minus 2. Those are exactly the representation that are both injective and have a discrete image. Okay, so let me define what discrete image means. So since the representation, the image of the representation is a subgroup of PSL2R. And we say it is discrete if the induced topology is discrete. So it means that the points of rho pi 1s, when you look at them in PSL2R, you can find a neighborhood which does not contain any other point of rho pi 1s, like point of rho pi 1s are isolated. So those two properties are actually really nice properties, which mean that rho is injective, means that it's really a representation of pi 1s, not of one of its quotients. And discrete image mean that, like, the discreteness in PSL2R means that when we'll make it act on various space, we will, depending on what it acts, but if there is a metric preserved, for example, then we will act properly discontinuously, which means we'll have a nice quotient. Okay, so those two space, we call them the C2 and C minus 2, we call them Teichmüller component. So this is the Teichmüller component of S, and here I'll denote the other Teichmüller component of S, the one labeled by minus 2. So they are exactly the same, except like you go from one another by conjugating a representation in one by an element in GL2R. But they have the same topology, they are exactly the same. And when I talk about the Teichmüller component, I talk about one of those two. Like no matter which one you choose. Okay, so in Teichmüller space, so to say it once again, if rho is in Teichmüller space, then rho is injective and have discrete image. Okay, so why do we care about this space? Basically because you can quotient it by PSL2R. This is just conjugation action. Like if I have two representations, I can conjugate one, and basically like, okay, quotient by this action, and you get the space of hyperbolic structures on S, not exactly like marked hyperbolic structures up to a nice equivalence. So this just means that we look at hyperbolic structures on S when we consider two the same, if we can deform one in another. And but yeah, this is basically a bit bigger than the space of hyperbolic structures on S. But we came from the point of view of just morphisms, and we now have the space of hyperbolic structures, and we have more than that. By this identification, the space of marked hyperbolic structures, we can now understand what it means to converge, because we know how it means to converge here. On Teichmüller space, we know what it means to converge. So now we can say a sequence of hyperbolic structures converge to a given hyperbolic structure. Okay, so to understand hyperbolic structures, you have to understand T of S, which is this nice space with representation only injective and with discrete image. Now comes the Hitchin component, which is kind of an analog to the for PSLNR when n is at least 3. So this is an analog of Teichmüller space. And the field that studied this is called higher Teichmüller theory. And it's called this way because it studies space that are analog of Teichmüller space. So first, the Hitchin component is one of the components of this space, which is the same as we saw before, except that we don't look in PSL2R, but in PSLNR. So this space has 3 connected components. Okay, I draw them as balls, but they are not really. Okay, we can label them different ways. Okay, and basically one of them, I will call it the Hitchin component. Okay, it's a special one. I will define in a moment how, and I will define it by giving you one representation in it, and saying the Hitchin component is the connected component of this representation. Okay, so just to be clear, it does not contain the trivial representation. The trivial representation lies in the connected component labeled by O, by 0. It does not contain anything like that. Okay, so for n even, it's basically the same story, except that we have 6 connected components. All right, and the labeling depends on the n, I would say, but for sure we can say that here. So it's it of S. Okay, we have it of S, and here we have it of S star. So once again, they're all really the same. And when I talk about the Hitchin component, I talk about one of the two, like they're really the same, and you go from one another by suitable conjugation. Okay, and here you have the trivial representation. So let me describe one representation that is in the Hitchin component. So there is a nice map from PSL2R to PSLNR, which is a representation of the group PSL2R. It's a group homomorphism, and I will define it by saying that I can make a 2x2 matrix. I can make it act on the space of homogeneous polynomials in two variables with total degree n-1. How does it act? So I will describe the action only on monomials. So for example, if I act on something like this, all monomials are of this form, okay, a suitable power of x times the suitable power of y, such that the sum of the powers is equal to n-1, then this should be equal to, we replace x by ax plus cy, and we replace y by bx plus dy. Okay, so if you do this, then a matrix in PSL2R acts on this space, and this space is actually a vector space of dimension n. So basically, we get an action of the on Rn. We can check that it has determinant 1, and so it describes a morphism from PSL2R to PSLNR in a weird way, but it does. And actually, this is pretty computable. Like here, I've written it for n equals 3. Okay. So here you have all the coefficients, take A, B, C, D, and you compute this matrix, and this is tau of n. So everything I will say here actually does not really matter about tau of n. The map as I define it here, you can take any conjugate of it. It's about the same, but still, at some point I would say something that is relevant to this tau of n, but not in this part. Okay, so there is a nice thing you can do. What nice thing you can do is like you can take J in Teichmüller space. So J goes from pi1s to PSL2R. And you can look at tau of n comma J. This goes in PSLNR. Okay, those are like well-defined maps and homomorphisms that have quite nice properties, and we can look at them. And actually, those are the first map that we consider to be in the Hitchin component. So a Hitchin component, or the Hitchin component, like I explained you the problem earlier, is a component of pi1s to PSLNR that contains a representation of the form tau of n circ J where J lies in Teichmüller space. So J can be any injective map with discrete image. But like if you have this, then they can be in two different connected components, and you might have you fix a J like this, J injective with discrete image, and you do tau n of J. You lie in a connected component of this space, and thus this component is called the Hitchin component. So this component attracted a lot of attention recently. There are various people working on it, trying to understand its geometry, and one of the question people try to answer is give a geometric interpretation of the Hitchin component. Like I said, that for Teichmüller space, it was hyperbolic structures. So for the Hitchin component, what can those be? Okay, so like in the Hitchin component, you have the function locus, which is exactly those representations. But actually, the Hitchin component, like here you have the, okay, let's draw it like this. Okay, the function locus should be something which is way smaller, like way smaller in terms of dimension than the Hitchin component. But most of the Hitchin component is not the function locus. Okay, so you can start with a representation like this and deform it. And if you start with a representation like this, you're on the function locus. And then you can start deforming it. So to be clear, this line, I will always draw this line to say the function locus. Okay, and then you deform, and here you have a nice representation, which is not the function locus. So in 2006, Labourie and Fock and Goncharov, 2003, and they proved that Hitchin representation have two nice properties that Teichmuller space have. They are injective and have discrete image, so exactly like Teichmuller. And this led to the notion of higher Teichmuller space. So a higher Teichmuller space is a connected component of Taiwanese G for G semi-simple Lie group. That contains only injective and discrete representation. So there are other examples of higher Teichmuller spaces except the Hitchin component, but like the Hitchin component was one of the first to be discovered. And for example, the maximal components. And people are trying to like generalize what is known from the Teichmuller component to those higher Teichmuller space. Okay, so this is a Hitchin representation. Now we talk a bit about lattices. So we take G to be a Lie group. Then there is something called the Haar measure. Okay, the definition is a bit technical, but all we need is that it exists. So there is a theorem that states that there is a unique measure up to scalar multiple, which is sigma finite and Borel, such that first it takes finite value on compacts, and second, it's invariant by left translation. So if I take a Borel subset, and I take J in J an element, and I push A by J, then I get the same measure. Okay, so this measure exists, just consider it to exist, then we can define a lattice as a subgroup gamma in J that is discrete and such that the quotient has finite measure, has finite area. So sorry, the measure of the quotient is finite. Okay, so this is pretty general. This allows us to like, if I take G semi-simple, then a lattice and gamma lattice, I can look at something called G mod K, where K is in G is a maximal compact subgroup. And then I can quotient by gamma. I must have got this wrong, maybe this way. So this will be of finite measure, because quotienting by k does not change anything since it's compact. And actually, if you want a quotient of j mod k with that look locally by like j mod k, but with finite measure, then you have to have it quotient by a lattice. So this is the way you construct geometric manifolds with finite measure. Okay, they are super important, and there have been a lot about them. It's like a pretty known concept, and that's, we're not trying to understand them much here. We're more trying to understand the Hitchin component here. Okay, so example. So if you want to construct a lattice in PSLNR, you can say, I look at PSLN Z, for example, matrices with Z coefficients and determinant 1. You can do the same for the symplectic group. Okay, here I put P in front, but we don't really care. So symplectic group are those that preserves a form J that is anti-symmetric. Okay, so you can notice already that those constructions are really arithmetic constructions, and there's a reason. There's a deep theorem that says that if the rank of your Lie group is high enough, then and your Lie group is simple, then lattices will always be built by arithmetic constructions. So, like, I can give you another example in PSLNR of a lattice. For example, I can consider SU n sigma z square root of d. Okay, what is this? So d is in okay, z plus, not a square. Okay, I look at the ring generated by the square root of d, and sigma acts on goes from z square root of d to z square root of d, and fixes z, send square root of d to minus square root of d. It's the field automorphism of q square root of d. Okay, and here we will define it as the matrices with determinant 1 and coefficient in z square root of d, such that if we apply sigma and transpose to the matrix and multiply it by m, then we get the identity. Okay, so this is a lattice. So this is a lattice in SLNR. And this is a non-uniform lattice in the sense that the quotient is not compact. For all the examples I gave you, the quotient is not compact, but it is of finite volume. So the question we try to answer here are, you take a lattice in G. Does there exist a Hitchin representation with the image in the lattice? And we know very few about that. To give you a hint, we assume it to be true in all cases, and we'd like to understand better the Hitchin representations that lie in a lattice. And I explain a bit more about that in the second part, where I give motivation about this question.